when does the ball reach its maximum height? What else do you think I'm going to ask? How long does it take to hit the ground or the water, okay? How long does it take for the ball to hit the ground? Or the water. If we're going to say it's a river, then whatever. You can put ground or water there. It doesn't matter. Understand? All right, now, because this object was thrown on Earth, and we are neglecting air, because we're not prepared to put air into the situation yet, right? Then we can model it with this quadratic equation, which we know looks like a parabola, right? And I said last time that before we can start the problem, we must determine what two things here. To start the problem out, this is the formula, right? But there are two things you must have before you can actually begin to answer any questions. Remember what they are? The initial velocity, that's what this was called, right? This was the initial velocity. That's the starting speed of the object. And then you also need to know this thing, which was the initial height. So the starting height of the ball. With me? Do you know either one of those? Yes. Okay, tell me which one you know. The height. The height? What's the starting height of the ball? 40 feet. Let's go with 40 feet. Even though if I was standing on a 40-foot bridge, then I would be a little taller than the bridge. So let's just say 40 feet. Is that all right? Close enough? All right. So we know that h naught is 40 feet. That comes from this. What else? Well, there's only one other number there, right? 24? That's the speed, right? Velocity is speed. Speed and velocity are almost the same terms. They do have slight differences. But in this class, speed, velocity, same thing. All right, so that is 24 feet per second. So I'm going to put a 24 right here. But there was something I told you in class about, I don't know if you remember this example, where I dropped one and threw one. Do you remember that? And I said, you know, obviously one's going to go faster than the other one. So what did I tell you about this right here? Something about the positive or negative. Do you remember? If it's going up, if the ball's going up or the object is going up, then that number will be positive, and if it's thrown downward, then it would be negative. So I'm going to place a positive 24 here, right? Okay. So I'm going to erase all this, and I'm going to rewrite that formula right there. H is equal to negative 16 t squared plus 24t plus 40. I want to point something out. On your homework problems, which you'll have for this section tonight, they just give you the formula. All right? They talk about a ball's thrown or whatever, a rocket is fired, and they just give you this to start the problem. So you don't have to actually do this on the homework. But on your exam, I will do it more like what I just put on the board. You're going to have to identify these two pieces. Understand? Okay. All right, so that's it. This gives us, this equation right here tells us how high the ball is, right? The height of the ball at any given point in time. So you provide me a t, and I'll tell you how high the ball is, right? For example, at t equals 0, at time is 0, where are we? 40 feet. 40 feet, and you can check that right here. T is 0, that goes away, we should have 40. We know that this is a parabola, right? And we know it opens down. So if I were to just draw something for you real quick here, the t is like the x is, the h is like the y was, and this point right here should be 40. Right? That's a y-intercept of this graph. Now, as time goes on, I throw the ball in the air, right? The clock starts, time goes on, what's going to happen? It's going to go up first, right? And then it's going to come back down and eventually hit the ground at some point in time, right? So let's talk about these three questions. How high does the ball go? What does that refer to in this picture? The vertex, right? This has something to do with the vertex. It has something to do with this point. And not, when we say vertex, the vertex is a point, right? An ordered pair. Remember the vertex is H and K? Y'all remember that? How high the ball goes is not the whole thing. It's one piece of that. Which piece? Is it the X or the Y? What do you think? The Y. Because think about this. The height, right? The height is the y-axis. And when you say how high does the ball go, that means you want to know how high this is, right? That's the y-coordinate of that point. So that's actually what here? H or K? It's K. So do you all understand that problem number 1, or part A, is asking you for K? Yes? This is asking us for K. We're going to have to find what K is. Keep in mind also that our answer here should be in what? What unit? Is that time or is that feet? Feet. It's the height of the ball, right? All right. When does it reach its height? Maximum height. When? When is time, right? Time is on this on the x-axis, right? Time is this way. So when does it reach its maximum height? That would correspond to this point right here, right? But that's actually what off the vertex? That's the H, right? Right, to get to this point I have to go out H, up K, right? Out H, up K. So this is asking me for H. Find H. And this answer will be in what units? Seconds, right? Because it's asking for time. How long? Time, right? How long till what? Till it hits the ground. When it hits the ground, how high off the ground is it? 0, right? Do you agree that when it's here, the height is 0? So what that means is in this equation, I'm just going to replace H with 0 and solve for T. Understand? So for here, this last one is telling you to let H be 0 and solve for T. All of these problems basically turn out to be this scenario. You're going to have the vertex involved. You're going to have what we used to refer to as the x-intercepts. Understand? How many answers am I going to get when I let H be 0? Can anyone tell me just by looking how many answers I should get for T? If I let this be 0, how many different answers I would get?
2.
I should get 2, right? Because this parabola actually goes backwards and hits over here, doesn't it? Now that answer that I get, I'm going to throw it out. Why am I going to throw that answer out? That's time, that's negative time, right? And that doesn't make sense in the physical problem. Right? There's only one time that makes sense, and that would be this positive answer. The negative answer, although it exists, does not make sense in the real world problem. Right? When I solve this equation, set equal to 0, this equation has no idea that we're talking about a ball being thrown off a bridge, does it? So it's going to provide me the 2 answers of the parabola. Only one of them makes sense to the problem I'm working on. All right. Are we clear on all this? We got to go do it now, all right? So what are we going to do first? Good. I'm not going to do part A first because I can't find K unless I know what H is. Remember how we found K? You had to find H first. So I actually have to do part B before I can do part A. Yeah? Okay, here we go. So let's find H. And to find H, we used a formula, didn't we? And to use the formula, we have to identify A, B, and C. So what is A for us in this problem? Negative 16. And on Earth, it'll always be negative 16. It has that negative 16 has something to do with gravity. B for us, 24, and C, 40. Okay. Bless you. All right, here we go. Oh, I should also point out, this is very important, all right? This H is not the H we're about to find. There could be some confusion there. This H represents the equation. This is the height of the function, right? The formula that we have to find this highest point, we called that point HK, didn't we? Okay, so there is some confusion there. That's why most books do not use H. They use D for like distance. I used H because H, height, usually makes more sense at this point. Like, to most people, H is easier to associate with height than D is, right? Okay. All right, let's get H. H, what's the formula? Negative B over 2 times A. That's the formula for H. I gave that to you, what, like 2 weeks ago? Right? That formula? All right. So what is this going to be for us? Negative 24 over 2 times negative 16, which is, oh, that sucks. 24 over, yes, it's negative 24 over negative 32. Negative over negative is positive, right? And then I can reduce that, right? I can reduce that? What goes into both of those? 8 goes in there, 3/4. So 3/4 is H. Now what would you have to do with 3/4 at this point if you wanted to continue with this problem? To get K, you would have to plug that into the original thing, right? But I am going to convert this to a decimal. Why am I going to do that? Because I can use a calculator, but because my answer needs to be in something that makes sense to me. So 3/4 as a decimal is what? 0.75. So that's equal to 0.75, right? And so let's answer part B before we go do part A. What was part B asking us for? How long till it gets to the maximum, right? How long? So the answer to part B is what? 0.75 seconds. That is the answer to part B. So if you're standing on a 40-foot bridge on planet Earth and you throw a ball up into the air and that ball leaves your hand at 24 feet per second, it will take 3/4 of a second for that ball to reach its maximum height. And then it starts coming down, right? That's how long it'll take. Feel like it'd be long? Well, 24 feet per second, that's pretty fast. Or is it?
No. Well, if you're going it, yeah, I think that.
Let's see. 2, 4, 8, 10, 12, 14, 18, 20. I don't know. I would say like from here to that wall is like 30 feet. All right? Maybe 30 feet. So what's 30 feet per second look like? I'm going to try not to hit anyone over there, all right? So let's say 1, 2, 3, 4, 5. That was about 24. That was about 30 feet a second. That wasn't that fast, you know? That was about 30 feet. It took about a second. This is obviously not a real scientific experiment. But if I said 1,000 feet per second, now that would be moving, wouldn't it? Yes? Yeah. Okay. What is the speed that we all are most familiar with? Like if I say to you right now that you hit a wall at 24 feet per second, would you live or die? You hit a brick wall. You're running and you hit a brick wall at 24 feet per second. Are you going to live or die? If I say 24 miles an hour, are you going to live or die? Let's try something else. What if you hit the wall at 50 feet per second? Are you going to die? 50 feet per second. How about 50 miles per hour? You'll die? See, we all have a good idea of what 50 miles an hour is, right? 50 miles an hour, you hit a brick wall at 50 miles an hour, you're probably not walking away, right? Feet per second is something we don't deal with on a daily basis. I wonder if there's actually a way we can get from feet per second to miles per hour. Yeah. I'm kind of going off topic here, but do y'all want to know how to go from feet per second to miles per hour or not?
Yeah, sure.
Half of you do, half of you don't. I'll do it over here real quick. It's very straightforward, but you have to know a couple of things. You're going to write 24 feet over 1 second. And don't like totally tune me out here, because you remember that section we skipped on conversion factors? This is what it is. All right, we will do this later. If I'm going 24 feet, for every 1 second I go 24 feet, what I need to do is first get rid of feet and turn it into miles, because that's what we like, right? Miles per hour. So you have to know how many feet are in a mile. Anyone know how many feet are in a mile? If you were to take 1 mile and measure out how many feet that is.
It's like 1,200 or?
5,280. 5,280 feet is in 1 mile. All right? So what I did here, notice I put the feet on the bottom and the mile on the top. So 1 mile is this many feet. I do that because now these feet units cancel. You with me? Now, I want to go from miles, I want to go from seconds to hours. How many seconds are in 1 hour? 3,600 seconds. So how many seconds in 1 minute? 60 seconds in 1 minute. How many minutes in an hour? 60 minutes. So 60 times 60, that's how many seconds there are in an hour. So there's 3,600 seconds in 1 hour. Why did I put seconds on top and hours on bottom? Why didn't I do it hours on top, seconds on bottom? See that? So look at what are the units that are left? What units did not cancel? Miles over hours, right? Miles over hours. And now I'm just going to get on my calculator. Someone get on their calculator real quick. Do 24 times 1, which you don't need to do. 24 times 3,600. Divide that by, what are these three multiplied together? It's 1 times this. Divided by 5,280. 16.36 miles per hour. So 24 feet per second is 16.36 miles per hour. That's how you convert from feet per second to miles per hour. So that's moving, but I don't think that's death into a brick wall. All right, sorry. Back to this. All right, A, that's part B, right? How long did it take to reach the maximum height? So we just found time, right? That this was 0.75 seconds to get from here to here, which was the maximum height. Got us to the maximum height. Now, what is the maximum height? We have to find K. Plug it in. So to find K, we're going to plug 0.75 into this for T. So it's going to look like this. Negative 16 times 0.75 squared plus 24 times 0.75 plus 40. Understand? Be very careful. You have your calculators. Make sure you do this properly. Square the 0.75 first. Whoa. You should have negative 16. When you square that, you should get 0.5625. Y'all get that? Anyone get that?
If we put it in the calculator like we did on top, would it be the same?
If, like the whole thing, you just got to make sure you type it all in correctly. Yeah, I mean, that's all going to come down to you and proper use of parentheses. And go ahead and do it and see if you get the same answer I get, okay? When you multiply these two together, that's 18, and plus 40. Is this 9, negative 9?
Yeah.
It is. I think that's negative 9.
Yeah, it'll be negative 9 if we multiply.
Yeah. So this is negative 9 plus 18 plus 40. So that's only what?
49.
49. Huh. 49 what? Feet. That's the height. That doesn't seem that big of a deal, right? Like I've got a ball on a 40-foot bridge. I'm throwing it into the air at 16 miles per hour, right? That seems like a lot. And it only goes up 9 feet and comes back down. right? It goes up 9 feet. Because I started at 40, right, didn't I? It went up to a maximum height of 49 feet, and then started its way back down. So the answer to part A, 49 feet. That's why it's so damn hard to get astronauts into space. It takes a lot of energy to break away from the gravitational acceleration of the Earth. You have to have a lot of force to get something out. All right? All right. We've answered part A and part B. What's part C? Let h be 0. So you're just going to set for part C, set this entire thing equal to 0. Negative 16t squared plus 24t plus 40 equals 0. And you have the pleasure of solving that quadratic equation. And I'm pretty sure that's not going to factor. So I think we're going to be stuck with quadratic formula here. Now normally our quadratic formula, we wrote it like, what, x equals negative b plus or minus square root. We've done that 1,000 times now, right? But I will point out, we are not going to write x equals. We're going to write what? What's our variable? T. Okay, so just remember, this is t equals this. So let's go ahead and write that down. T is equal to, what's negative b? Negative 24 plus or minus the square root, b squared, 24 squared. So this is going to be some calculator time here. 576? Minus 4 times a, which is negative 16, times c, which is 40. All of this over 2 times negative 16. I'm just plugging stuff in, right? Did you have to do this on your homework at all? Yes. Yep, there were some times where you had to use a quadratic formula, right? So you want to get pretty comfortable with this and not make those little mistakes that can happen here. So this next line should read negative 24 plus or minus square root 576 minus. Now, remember, I do it this way. I cover up the negative sign. There it is. And then I put these three numbers together. These three numbers together would be a negative number. It actually comes out to be negative 2560. And then all of that over negative 32. And when you see minus a minus, this really turns into plus, doesn't it? That's a plus. So go ahead and do 576 plus 2560. So underneath that root, you should have 3136. Is that what you get? Yeah. Anyone else get that? Okay. And what am I going to do with this? Once I'm here, am I going to box this up as my answer? No, I'm going to actually find this as a decimal, right? 3136 over negative 32. I take the square root of 3136. Oh, it's perfect square. Wow. It's 56. I made this problem up completely, so I'm surprised to see it come out to be a clean number. I told you all about my daughter who's 7, who's trying to learn her perfect squares. And she keeps pushing me to learn more, and I'm like trying to hold her back. She's like, I want, what's 16 times 16, Daddy? And I'm like, I don't know. I'm like breaking my calculator out, and I'm not trying to hide it from her, I'm like, hold on, let me check. All right, so that's a perfect square. I mean, I couldn't have planned that to happen like that. So, all right, let's continue. This is where I do this, right? 2 different answers. So on the top one, I'm going to do negative 24. I'm going to do plus 56. I'm going to divide this by negative 32. That should be, what's that up there? 32?
Yeah.
32 over negative 32, which is negative 1. Wow. All right. And then the other one, what would I get if I did negative 24 minus 56 over negative 32? So negative 70, negative 80 on top.
Yeah.
And then over negative 32, which is, what is it? 2.5, like dead on? Wow. There are two answers. So what do these numbers represent?
Whether it's long.
Yeah, it's our x-intercepts, or our t-intercepts, really. But which of these is the one that makes sense? 2.5, right? This negative doesn't make any sense to us. So what is it, 2.5 feet, seconds, miles, what is it? Seconds, right? 2.5 seconds. That's the answer to part C. You take a ball on a 40-foot bridge. You throw it into the air at 24 feet per second. It will take 0.75 seconds for it to reach the maximum height. The maximum height will be 49 feet. It will then proceed to fall down all the way down to the ground. It will take a total of 2.5 seconds for that to happen. Got it? That's the way it works. You can do that for any object on Earth. And now, we said you take air out, right? You have to take air out of the equation. But really, it turns out, if you're dropping a ball or a brick, the air resistance really doesn't make that much of a difference. If you're dropping a feather in a bowling ball, yes, air will play a factor. But if the objects are pretty mass, have a lot of mass to them, then it's negligible, the difference. All right. Questions? You think you can handle some word problems like that? I guess you'll have to practice, right? With your homework, yep. So for your homework on this, you're going to be looking at page 77 and 78, problems 1 through 7. Yeah, numbers 1 through 7. So it's everything in that assignment. And remember what I said, they provide you with the formulas right up front. Right? They give those to you. So you don't have to plug things in. You just use the formula they provide you and answer the questions. All right, we're going to move into polynomial functions, but we need to talk about the test. All right, let's look at the calendar here real quick. Our first test is not scheduled until November 1st. That's still a ways off, isn't it? Do you all agree with that?
Yes.
What do you say? No? You want to? How many of you want to keep it November 1st? It's okay if you do.
What do you plan on moving it?
Well, I'm thinking of moving it maybe a week, October 25th, a week ahead of time. So that would be not next week, not next Tuesday, but the following Tuesday. What do y'all think? That sound all right? Yeah, then you can have your Halloween to do whatever you want to do, right? If not, November 1st is the day after Halloween, isn't it?
Yeah.
Anyone want to come in here and take a test the day after Halloween? No, probably not. So can we do that officially? Okay, let's say exam 2 is officially moved. It's going to be the 25th. Now, what it will cover, we will discuss that. We have today, and we have all of next week. I won't introduce Much more. Just I'm going to do one more topic, and then that's it. That'll be all that'll be on the test. So it'll be whatever's left today. We'll cover whatever I cover on Tuesday, and then Thursday. Let's spend all of Thursday talking about the test. Fair? Okay. Do you remember the question I ended class with last time? We had the rock on the building, right? Didn't we? Dropped a rock on the building. How long did it take for that rock to hit the ground? It was a 1,200-foot building, wasn't it? We did solve it all the way, didn't we? Please check. We did? Did we get a decimal answer? 8.6. Took about approximately 8.6 seconds. Right? All right, so I want to say something about this because there's a reason why I picked that problem. I picked that height for that building. That's a pretty tall building. On September 11th, remember, obviously, what happened? I've always looked at that day as being, I mean, of course it was a terrible day, but there's actually some amazing physics that happened that day that most people don't think about. If you just drop a ball or a rock from that height, it's going to take about 8.6 seconds for it to hit the ground. Now, the World Trade Center was a little taller than this if you include like the antennas and stuff on top, but roughly 1,200 feet is good enough, all right? So when the buildings finally did collapse, right, how long do you think it took for that actual, like for the top of the building to actually come all the way down?
It took a lot less.
Was it more or less than this? What do you think? Less? Everyone's less? More? Think about it like from a physical standpoint. If I drop this ball, the only thing acting on it is gravity, right? It's going to take 8.6 seconds for it to hit the ground. There's nothing slowing it down other than air. When the building collapsed, what was slowing it down? Itself, right? It actually had to destroy itself on its way down. So we're talking about huge columns of concrete, huge beams of steel, right? That as it collapsed, it had to completely pulverize that, turn the concrete into dust, turn the steel into, bend it to the point like it's like a paper clip, right? You would think that that would slow it down, don't you think? Each floor had to be compressed and compressed and compressed as it went down. Doesn't it seem like it would slow it down? It actually took right around 8.6 seconds. The point is what we call potential energy. All the energy that was stored in that building, all the energy it took to get everything built, right? All those guys up there building it way back when, taking all that steel to the top. Every time you lift something up, you're storing energy in it. Right? If I take a brick right now and I pick it up off the ground and I let it go and it hits my toe, you're going to feel that, right? You're feeling the energy that's stored in that brick being transferred to your toe. When this thing went, all that energy that had been stored in it, its potential energy, was converted to what we call kinetic energy. And we're not talking about little amount of energy, we're talking about a tremendous amount of energy. So much energy that the process of crushing itself did not affect how long it took for it to fall. It was almost like it was a rock just falling. To me, that's always been amazing. That amount of energy didn't. Do y'all know what I'm saying? I mean, if I just ask you to take a cardboard box and crush it, I mean, that would take some force, right? Imagine trying to crush concrete columns, steel columns. That's a lot of energy.
Like an explosion.
Yeah. Yeah. Okay. All right, so, and then there's one other thing I wanted to talk about. I'm just full of random information in this class. I apologize. Trust me, if this were my 1414 class, I wouldn't be going off on all these tangents. But I find this an opportunity for you to like peek into the world of math a little bit. What happens if I'm standing here? This is tied into the parabola, and I have a gun. There's my gun. And I shoot a bullet flat, parallel to the earth. Shoot this bullet out, right? There it's going. What's going to happen? It's going to fall, right? What's wrong? You don't like my gun? Okay. All right, so it is a Red Ryder BB gun. There. Is that a little better? I don't know. There. Is that a little better? Has a stock now? All right, so I shoot this bullet. It's going to fall, right? Eventually, it's going to hit the ground. The path that it travels in is a what? Parabola. It's a parabola. It is a parabola because it's a falling object on Earth. It's going to fall. So here's my first question to you. If I have two bullets sitting here, let me get on this side so I'm like the guy. I shoot this red bullet out a gun, and I drop this bullet, I'm just standing here holding it, and I drop this bullet and I shoot this bullet out. Which one hits the ground first? Same time? You seem pretty confident in that. Any of you think the bullet will take longer? Most people do, so if you feel that way, don't feel bad, all right? If I shoot this bullet and I drop this bullet, they will hit the ground at exactly the same time, which means that the horizontal speed has nothing to do with how fast it's going to take to fall. All right? So, what if I shot this bullet out so fast that as it was trying to fall, see, if I shoot the bullet out faster, if it's a faster bullet, it's still going to be a parabola, right? Still going to be a parabola. It will fall, but it'll go further before it falls. It won't take longer to fall. It'll just go further before it actually hits the ground. Understand that? Okay. So these like sniper rifles and stuff, very, very, very fast bullets. That bullet will be way out there in a very short amount of time, as opposed to like a handgun where the bullet doesn't come out as fast. All right? So what if I shot a bullet so fast that as it tried to drop, as it was starting to drop, well, we live on the Earth, right? The Earth is flat. The Earth is round, right? So let me redraw this picture. I'm standing on the Earth, and I shoot a bullet out my gun, and it's so fast that as it drops, as it starts to drop, the Earth is actually curving, because the Earth is curved, right? So it's curving, as it drops, it's curving, and the Earth is curving away from it, and it keeps trying to drop, but the Earth is curving away, right? And the other side of the Earth, you're not upside down. The gravity is not reversed, right? Your feet are still on the ground, right? So it continues to go around. It tries to drop, but the Earth curves away, and it continues to do that, and it just, what happens when it comes back around? Hits you in the back of the head, right? You killed yourself, Dad. What is this? This is what a satellite is. This is what, when we say we put things in orbit, right? When they send a satellite up and it's sitting there in orbit, that's exactly what it is. We shoot it out so fast that we turn off the rockets and then all of a sudden it's falling. It starts falling towards Earth, but the Earth is starting to curve away from it, and then it's just stuck in this perpetual falling motion. And that's orbit. It's kind of interesting, right? Like you don't have to power these satellites that are out here. That's a satellite. Is that okay? That's a satellite. That's okay. These satellites don't have to be powered as far as propulsion is concerned. They're just falling.
Do they ever get closer?
It's not perfect because Earth's not a perfect sphere. So in theory, they should go forever, but because the Earth's not a perfect sphere, they do start to lose track a little bit, and they will make adjustments. They do make adjustments. And then sometimes there's some out there that we have no control over them, and they just eventually come crashing back down to Earth. But the thing is, they're going so fast that when they hit out here there's no air. And then when they get closer to Earth, there's air. And if you've ever stuck your hand out the window at 60 miles an hour, right? You're like driving, you go, like your hand goes backwards, right? Like imagine coming in and hitting air at like 16,000 miles an hour, which is how fast these things go. What's going to happen? It's going to destroy it. And it'll vaporize it. The friction of the air rubbing on the metal will just like turn it into smoke, fire. It's done. All right, we're getting way, way off topic. That's a parabola. A parabola that follows around the curvature of the Earth, that's orbit. These things are not, I just want you to see, these are not like magical, mystical things. These are very much tied into mathematics in some way.
Graph a parabola or something like, or would it be parabola? Does it never touch this?
It would never hit the Earth, so it wouldn't be a parabola.
Okay.
Yeah. Yeah, once you start getting to that, you get to like this limiting point where that model doesn't work anymore. That model is going to work as long as this object is coming back down to Earth, right? All right, polynomial functions. Let's move on. We're going to start talking about other things totally unrelated. That's somewhat related, right? I think somewhere deep inside, I want to teach physics. Somewhere inside of me. All right, polynomials. Now, we've actually dealt a little bit with polynomials in the very beginning of the class, but what we're going to be looking at here are polynomial functions. I forgot to put that there. So let me just start this with reminding you of a couple of things. If I were to ask you right now to take a look at this and sketch it, draw that for me, what would you draw me? A line, right? This would be a line. And I hope everyone here would be comfortable drawing a line. You had to do it on one of your tests, right? Now if I come in here and I say, hey, draw me this. What are you going to draw me? A parabola, right? This is going to be a parabola. And what I want you to see on these is that in both of these problems, you have x as your variable, right? X is your variable. The m and the b are just numbers, right? The m was your slope. The b was like where you hit the y-axis. So these numbers were always provided to us. In this problem, x was your variable. A, b, and c were just numbers. So x being the variable here, the power on x was 1, right? The power here on x was 2. What about if we go to 3, or 4, or 5, or 6, or 28, or... It doesn't matter how high the power goes, right? A polynomial function is any function that has x raised to any power as long as the power is a non-negative integer. So let me explain. Polynomials, examples, all right? So here's some examples. Y equals 4x cubed plus 3x squared minus 7. That's a polynomial. That's a 3. This right here. Is a polynomial. And I could go all day long. I could just start writing things out. That's a polynomial. Poly means many. Nomial means a single term. So this right here is what we call a monomial. It's a single term. This is another single term. This is another single term. Polynomial means many of these. So we have 1, 2, 3 of them there, here 3 of them, here 4 of them. Right? So this is what polynomials look like. The highest power of x that you see, here it would be 3, here it would be what? 8. The highest power you see here? 4. That is called the degree of the polynomial. So the highest power of x is the degree. The degree is the highest power of x that you see, all right? Everyone clear with that? This is a degree 3 polynomial. This is a degree 8 polynomial. This is a degree 4 polynomial. There is no limit to how high the degree of a polynomial can go. You can have a polynomial that has a degree of 1,257,962. You could, right? Now there's another term, another definition that we need to be aware of with these polynomials, and that is what's called the leading coefficient. You'll see how these are going to come into play in a second. The leading coefficient is the number in front of the highest power of x. All right, so for this example over here, what is the leading coefficient of this first one? 4. That's your leading coefficient. What's the leading coefficient of this one? -1. Good. -1 right there. What's the leading coefficient of this one? 1. I'm going to put another one up here. I'm going to try and trick you. I don't think I'm going to, but let's see if I can. What's the degree of that polynomial? The degree. Highest power of x. 5, right? The degree is 5. What is the leading coefficient? -3. It's the number in front of the highest power of x. Here's your highest power of x. It's the number in front. So -3 would be your leading coefficient. Understand? Okay. So the order doesn't matter. However the order is scrambled up, you're looking for the highest power of x, and then you're looking for the number in front of it. Now, why is it that we would want to know these two pieces of information? Well, it has to do with the graphs of these. And I'm going to talk about that now. Like, this is what polynomials look like. We know 2 new things about them, what's called the degree and the leading coefficient. Those are definitions. And now let's talk about their graphs, because we're actually going to graph these. Okay, we're going to, just like we graphed lines, just like we graphed parabolas, now we're going to graph polynomials. Now we're not going to get too heavy into it, all right, but we are going to try. Graphs of polynomials look like smooth, curvy. Is curvy a word? Is that the way you spell it? Roller coasters. You know what a roller coaster is, right? You ever been on a roller coaster? Right there. That's what polynomials look like. They're smooth, they're curved, and they look like roller coasters. Now, I need to put a little asterisk under here. If the degree is greater than 1. Remember, the degree is the highest power of x, right? What if the highest power of x is 1? Then your polynomial would look like this. Right? That would be a degree. The degree of this would be 1, wouldn't it? And what is that if I graph it? A line. And lines aren't curved. Lines are straight, right? So it'll look smooth and curvy as long as the degree is greater than 1. So what about a parabola? What does that look like? Is that smooth? Smooth meaning there's no like breaks or jumps or like any jagged edges on it. Remember I told y'all not to do this for a parabola, not to make a corner? That would no longer be smooth. You would have like this sharp corner up at the top. So this is not a polynomial. This parabola is nice and smooth and curved, right? Does it look like a roller coaster? That's a pretty boring one. And then you're done, right? But that's what it looks like. Now another thing about these pictures, right, is that they go forever in both directions. So I'm going to just draw some examples of polynomials. I might have a polynomial that does this, and the arrow would imply to you that it just continues to do that in that direction. So this arrow means that just continues to go up, out of the room, out of the building, up forever. This arrow would mean it goes down, keeps going down forever and ever. Understand? So I could have a polynomial that looks like that. It could do this. You could have a polynomial that does that. And anything you can think of that is smooth and curvy and at the ends goes up or down forever. That's the main thing. At the ends of these polynomials, it's either going to go up forever or down forever. Same thing on this side. It's going to go up forever or down forever. Now in the middle, it's going to do some wavy stuff. That middle part is the hardest thing to figure out. All right? Think about a parabola. Is a parabola a polynomial? Does it do that? On the left end, what does it do? Goes down forever. What does the right end do? Down. If I draw it as a parabola that opens up forever on the left, up forever on the right. Understand? All right, so I wonder if there's an easy way to just look at a polynomial function and know what it does. And the answer is yes. There's a very simple way to just look at the function and or the equation and be able to know what it does at the ends. All right, so we actually have a name for this. We call it the leading coefficient test. And you'll have to be able to do this. The leading coefficient test. I will refer to this from now on as LCT because I don't like writing leading coefficient test over and over and over. What this test does, all right, just so you know, this test tells you the left and right behavior of the graph. Did I spell behavior right?
No.
What am I missing there?
Take out the U.
The what?
The
No
U.
U before the R.
Yeah, you're there. Just
This?
Yeah.
Really?
Yep.
That's why I'm not an English major. I don't. Have I stressed to you how much I don't like the English language? I can't. Okay. All right, we good? This test is going to tell us what the left and right hands do, but I have to tell you what the test is. Here's what it is. You're basically going to have 4 different possibilities when it comes to a polynomial function. 4 outcomes, and that's it. Here they are. One outcome is that the left side could go up and the right side could go up. And in the middle, I'm going to put a question mark, meaning, well, it could do some waviness and do things in there. This is just telling us the left and right hand side. That's one possibility. Okay? What do you think another possibility is?
Left up, down, right.
Left up, down right, right goes down?
Yeah.
I could have that. Let's do this flipped over. What if both sides went down? Is that a possibility? Write them exactly the way I'm writing it. Put this one on top of this one. Then I could have left side down, in the middle it could wave around, and then the right side could go up. And there's only one other thing it could do. The opposite of that, which would be left side up, right side down. Okay? Y'all see the four possibilities? Nobody can come up with any other combination than that, right? That's it. Since there are four possibilities, I'm going to make a table out of this. And I'm going to tell you what it takes for each of these four things to happen. For the first one to happen, what we need is the degree to be even. I'm going to put D for degree. Is that all right? The degree of the polynomial is what? What is the degree again? Highest power of x. If the highest power of x is an even number, what are even numbers? 2, 4, 6, 8, 10, 12. So if the degree is even, it's going to do this, maybe. There's one other thing that has to happen for it to do this. The leading coefficient must be positive. If your degree is even and the leading coefficient is positive, you will go up on both sides. Got it? It'll do this one down here if the degree is even, but this time your leading coefficient is what? Negative. See, that's why when I was showing you what a polynomial was, I was pointing out the degree and leading coefficient, because those things will dictate how our polynomial behaves when we graph it. This will happen if the degree is, what do you think?
Negative.
Odd. If the degree is odd, what are odd numbers? 1, 3, 5, 7, 9, right? And the leading coefficient is positive, it'll do this. And if the degree is odd and the leading coefficient is negative, it'll do this. You have to remember that or put it on a cheat sheet or something, all right? Now, I think there is an easy way to remember this, all right? You may not think this is easy, but let me show you. Do you know what x squared looks like? What does that look like? Parabola, right? Isn't that a parabola? Which way does it open? Up. So does everyone agree that opens like this? That's what that would look like? What's the degree of this? What's the degree of the polynomial? 2. That's an even number, right? What's the leading coefficient? 1. That's positive, right? So if you have an even degree and a positive number, it's going to look like a parabola. What would happen if I changed that to negative x squared? Still a parabola, right? But this time, what? Negative in front makes it go down. So that would be this. That helps you with this one. This one, not so much. You'll just have to remember those. But it's the same thing. Do you see that it's just this one flipped over? Like this is going down on the left, up on the right. And then that's what happens if you have a positive leading coefficient. If it's negative, it flips. It goes like that. All right, so you think now if I give you a polynomial, you can tell me its left and right behavior. Let's try it. Find the left and right behavior. I don't want to spell it that way. My hand does not want to do that.